Good morning and welcome to this next lecture on vibrations of plates and shells. We are looking at the modes of a circular ring, and we had found the two equations that were relevant, and we put in the solutions, found the matrix, and the problem was done. But as I said, we are going to try and get some more insight out of this set of equations. So here we are. So last class I said, in this expression over here, suppose n square d by s square is very small, much smaller than k, which can happen for small n values. Okay, that means n equal to 0 and 1 maybe and 2 maybe. Okay, so then what happens is that for k2 by k1 squared is equal to, just from here by dropping this term, 4n square by a square n square minus 1 whole squared by n square plus 1 whole squared. And if I drop n square d by s square, I get k square, but there is a k on top, so I am left with d by k. But again you can see that there is n square d a square and k. So we said n square d by a square k is much less than 1, right? And for small values, when n is 0, this is 1, right? This is n is 0, this is actually 0. Okay, and when n is 1, also that is 0. Okay, for n2, this will be, 2 square is 4 plus 1 5, 25, and 4 minus 1 3, 9 by 25 into 4. Okay, 9 by 25 into 4. Okay, now what we are saying is that n square d by a square k is a small value. Okay, n square d by a square k is a small value, and therefore the small value multiplied by the ratios that we get over here. For n0 we get 1 by 1, for n equal to 1 we get a 0, for n equal to 2 we get 9 by 25. Okay, so this value multiplied by a small value here is a further small value. So I can take this to be an epsilon quantity. Okay, if that is an epsilon quantity, then omega n1 square can be written as k1 by 2 into 1 minus square root of 1 minus epsilon. Okay, and epsilon is a small quantity. If I do a binomial expansion of that, I get a k1 by 2 1 minus epsilon by 2. So I get k1 epsilon by 4. Okay, so this becomes equal to let's see, k1 by 2, okay, into epsilon by 2, okay, which is twice k2 by k1 square, okay, which is equal to k2 by k1. Okay, this is epsilon, so epsilon by 2 is 2k2 by k1 square. So 2k2 by k1 square into k1 by 2, that is k2 by k1. So k2 by k1 now is n square, so n square minus 1 square by a6 rho h square dk a square rho h by n square plus 1 into k. Okay. Now what happens? Now, okay, so rho h omega n1 square, first set of natural frequencies. If I take that, I get 1 rho h comes up here, 1 rho h cancels, so I get this, okay, and I get n square minus 1 whole squared by n square plus 1. This is done, this is done. Then I have a fourth over here, so I will write this as n square d by a square. I bring a k and I bring a k over a square. Okay, so n is small and n square d by a square k is also small. Okay, so if for such a situation, what happens is, this is, we can say, is much less than k by a squared. Okay, so this is of a small number, so it will bring down this number. So this is much less than k by a square. Okay, now, okay, so that gives me the magnitude of omega n1 square. Now, what about the ratio a n1 to b n1? Okay, so if I take one of those terms, if I take one of these equations, okay, once a natural frequency has been substituted, this matrix is singular, so I can compute an by b1 bn using one of these expressions, okay, either this equation or that equation. So let us see, an 1 set by bn 1 set ratio can be written as rho h omega n1 square minus n square by a square into d by a square plus k divided by minus n cube d by a fourth minus n k by a square. Okay, minus n cube d by a 4 minus n k by square. So we get that minus n k by a square. Okay, now what we have here, is if I separate out here in the denominator n square n by a square then I get n square d by a square plus a k. Okay, let me check the sign here. It will be plus. It will be plus. It will be plus. Okay. So now again I have n square d by a square in k. So this is small compared to k. Okay. And if n square d by a square is much less than k, then d by a square also we can consider much less than k for small values of n. So I am going to drop this in the numerator, I am going to drop this in the denominator. So we get rho h omega n1 square minus k n square by a square by n k by a square. Okay. Now if you recall, somewhere here we said that rho h omega n1 square is much less than k by a square, and therefore this is much less than k by a square into n square. So this now ends up as minus n approximately after all the approximations. Okay. So a n1 by b n1 is approximately minus n for the first set of natural frequencies. Okay. Now omega n2 square is given by, okay, if you see omega n2 square is given by, this is a small quantity. If we ignore, this is k1 is given by k1 and k1 and this k1 is this value, and we enforce the approximation. So what we get here is k1, which is n square plus 1 by a square rho h into k. Okay. So now what is an2 by bn2? That is equal to what? Okay. That becomes equal to rho h omega n2 square, which is n square plus 1 by a square into k, okay, minus n square k by a square as before divided by nk by a square as before, nk by a square as before. Okay. So this becomes what? N square k by a square is gone, I get k by a square and I get nk by a square. So this is approximately 1 by n. Okay. So if I make a note here, let's see if I make a note here, an1 by bn1 is equal to approximately minus n, an2 by bn2 is approximately 1 by n, and I have a straight number here, omega n2 square is equal to n square plus 1 by a square rho h k and omega n1 square is this. Okay, let's just put it here, omega n1 square, omega n1 square has n square in the numerator and n square minus 1 n square minus 1 on the numerator and other terms. That is all we need here. Okay. So, now let us see, let us see let us say that n equal to 0, n equal to 0. Okay. So, what is omega 0 1? That is 0, omega 0 1 is 0. Okay. What is a 0 1 by b 0 1, which is actually 0. Okay. That means a 0 1 is 0 and b 0 1 can be anything. Okay. B refers to which modes? B n refer to the torsional movement. Okay. So, I have a natural frequency of 0 and I have no radial displacement because a 0 1 is 0, no radial displacement, and I have a displacement that can be anything in the torsional direction. So, what sort of a displacement is this? Okay. Once you have 0 natural frequency, it is a rigid body mode. So, this is a rigid body mode in the torsion, That means this ring keeps rotating this way, no oscillations, no oscillations. Okay. Next, we have omega 0 2, okay, n equal to 0, but we look at omega 0 2. What is omega 0 2? This is not 0, it is k by a square rho h, not equal to 0. Okay. And what is it? I have a 0 2 by b 0 2 is equal to 1 over 0, which means b 0 2 is equal to 0. a 0 2 can be anything. And what are the a n modes? They represent the radial movement. Okay. So, now what do I have? I have oscillations, right? I have oscillations and I have pure radial motion. I have pure back and forth radial motion. That means the radius moves out uniformly and it moves in uniformly at some natural frequency. So, this is called the breathing mode. This is the breathing mode of the ring. Okay. Now, we have looked at n equal to 0 above. Now, let us look at n equal to 1. N equal to 1. Okay. So, when n equal to 1, okay, omega 1 is 0 again. Okay, so omega 1 is 0, and what is a n1 by b n1? It is minus 1. It is minus 1. So a 11 by b 11 is equal to minus 1. That means if my u31 is equal to a cos n theta, then u theta 1 is minus a sin n theta. Okay, so let us say a11 and a11. Okay, so what sort of movement is this? So let us see here. So this is my ring, and we will measure theta from here. Okay, so n is 1. Okay, n is 1. So this is a cos theta and a sin theta. So at theta equal to 0, I get a radial movement here. I get a radial movement here. Okay, but no torsion. There is no torsional movement. No torsional movement, only radial movement. At theta equal to pi by 2, theta equal to pi by 2, there is no radial movement, but there is, if I consider this to be my positive theta, positive torsion direction, at theta equal to pi by 2 I get minus a11. So positive would be this way, negative is this, so I get minus a11, so I get this movement of the ring. Okay. Next, at theta equal to pi, okay, theta equal to pi, I get a11 cos pi, which is negative. So positive radial movement is in this direction, negative radial movement is in that direction. So there is a movement in that direction. Okay, there is a movement in that direction here. Radial movement, negative is like this. Whereas at theta equal to pi, torsion, there is no torsion, sin pi is 0. And at 3 pi by 2, okay, cos 3 pi by 2 is 0, so there is no radial movement, whereas sin 3 pi by 2 is negative. Okay, so that negative and this negative make it positive, so I get a positive torsional movement. So what sort of movement is this? This is the oscillation in this direction. I'm sorry, this is just pure translation. It's a rigid body mode. One word can change everything, pure translation. The natural frequency is 0 here, so no oscillations. No oscillations. And 4, this represents non-oscillatory pure rigid body translation. Okay. Next, n is still 1. N is still 1. Okay. So let us look at the second set, omega 1 2 set. Okay, omega 1 2 set again, for n equal to 1 is not 0. Okay, it will have some value whatever it is. Okay, 2 by a square rho hk not equal to 0. Omega 1 2 square is not 0, and for n equal to 1, a12 by b12 is equal to 1. Okay, so a12 by b12 is equal to 1. So what is it now? u3 at 1 is a12 cos theta, and u theta 1 is equal to a12 sin theta, okay, because p12 is equal to a12. Now if I draw it here, is my theta 0, okay. At theta equal to 0 again, I have u3 as a12, so u3 has some value here, okay. Torsion is 0 at theta equal to pi by 2, I have no radial movement, okay, and I have pure positive torsion, so I have this movement here, okay. At theta equal to pi, I have negative a12 movement, so I have this movement here, okay, and no torsional movement, okay. And then at theta equal to 3 pi by 2, cos theta is 0, sin theta is negative, so this is this way, negative torsion, and omega 12 is not equal to 0. So this is an oscillatory movement, okay. So you can see both happening here. In the radial sense, this ring is oscillating back and forth. This ring is oscillating back and forth, okay, back and forth, okay. In one instance both ends are like this, in another instance both sides will be like this, and so forth. But when it is like this, the torsional points are bunching over here, okay. I will show you in the animation. So as the ring moves forward, in this direction, the points, the torsional points are accumulating over here. This becomes, so there is compression here and there is rarefaction here, there is extension here. On the other side, when this movement happens, okay, then that means when the ring comes like this, then the points accumulate over this side. That means there is compression here and tension here, okay. So both are happening, okay. So what now I will do is I will show you some animations, okay. I will get back to the other screen and show you some animations to give you some physical feel, okay. So let us see over here. Okay, so let us open ring accurate maybe, okay. So I am showing you N3 over here already. So let me run and see. Okay, I hope you can see what's happening. Okay, so you can see the N3 movement, right, like a club. You can see at instance it forms that. Along with that there is in plane movement, okay, there is in plane movement of the particles, okay. So let me see if I can exaggerate this movement. If I exaggerate, it becomes a bit unrealistic. So let me do 4 or something. The problem is that the particles will collide and move into each other, so it is unrealistic, but you will get a picture of it. Okay, now you see how there is both in plane movement within the ring of particles, at the same time they are moving outward also, okay. So please ignore these anomalies, because to accentuate the display, I have given more amplitude, so the particles are crashing into each other. So that part you ignore, but this is now clear how it is a coupled motion now, N3 coupled motion in torsion and in radial movement, okay. So I will keep it this way so that it is visible. So let us do N0, let us see if I can do N0. That should be purely 0 or O? 0, okay. So let us see here. So this is purely radial movement, okay. So it is purely radial movement. Omega 02 purely at a certain frequency. Now let us do n equal to 1 over here. You see how it oscillates, okay, omega 1 2, right, see oscillate, but as this movement occurs this way, particles are getting closer here, and as it moves this way, particles are getting closer here, compression is happening here, okay. So the radial movement is happening and in plane torsion movement is also. So you see these points are coming together here. In this case, points are coming together here. Okay. Now let us do maybe 2, which is an ovaling mode. So that is an ovaling mode, okay. You see how compressions line up in one place, tensions line up in another place. This is exaggerated, as I said, you do not get this much displacement, okay. Now let us just do a very high order mode, let us do 5 maybe. So the extra things are anomalous, okay. So if I make it realistic, if I reduce this value back to 1, then you do not see the displacement, but that is largely what happens. Here also you see quite a bit, okay, yeah. So the particles are crashing into one another, which is not. Okay, so that's how a ring looks like in its modes. Okay, so time is up for this lecture, so let me close it here. We'll start looking at a cylindrical shell in the next class. Okay, thank you.